Congratulations to everybody. You've made it to the top of the mountain for this semester. And the last problem that we are going to solve together is going to make use of almost everything that we've done during the course of our semester together. We are going to use the results from energy balances and entropy balances. We're going to use the equations that we've derived to look at the change of entropy of certain processes and the change in enthalpy of certain processes. We're going to also use our knowledge of how cycles work. And so, this problem in another semester was the project. So typically in a non-COVID semester where we didn't have to play games with dates and people could actually work together, side by side, I really like having a project, and I really like developing a project just like this that takes advantage of everything that we've done over the course of the semester. Now, since we couldn't do that, let's do this project together, okay? And I was inspired to create this problem by a paper that I read a few years ago that is based on a solar thermochemical water splitting heat engine, which is obviously not something that you would normally cover in our class. But I think it's a really good example of how we can use the thermodynamic fundamentals that we've built over the course of the semester to analyze almost any system, whether it's a heat engine or something else. And the way that this thing operates is quite interesting to me, actually. So the idea is that we're going to use solar energy to split water. And in this process, water's fed to one side of a rotating drum. And you have two reactions that happen. And you're really just manipulating the conversion of iron oxide between the magnetite phase, which is Fe3O4, and the wustite phase, which is FeO. And what happens is that if you think of the start of the process as having the iron oxide in the magnetite phase, so that's the Fe3O4, it's at the oxygen electrode at the top left of the picture that I'm showing here. Essentially, this oxide is thermally unstable. And so you want to use concentrated solar to increase the temperature. So you can heat it up and increase the temperature to the point where you completely decompose the magnetite phase to the wustite phase. So you go from Fe3O4 to FeO. And so you change the oxidation state of the material so it gets reduced. And so you have to release oxygen, right? So you're oxidizing the oxygen atoms in the lattice, and you get molecular oxygen out of this. And so if you look at this, we have Fe3O4 goes to FeO plus 1/2 oxygen. And this drum is rotating. And so these solids are kind of deposited on this drum. And what happens then is that as you go clockwise on this diagram, right? So you form the FeO phase here. And as the drum rotates, it reaches these fins. And the idea for the fins is that you would remove enough heat to reduce the temperature. So when you get to here, we're going to assume that you have only FeO, that you have complete conversion of Fe3O4 to FeO. But now you have really, really hot FeO. And if we're going to think about this as a chemical cycle, we need some way to get back to Fe3O4, and we're going to do this over and over and over again. So this reaction that we just underwent was endothermic. The reaction that we want, the reverse reaction, or not exactly the reverse reaction, but to take FeO back to Fe3O4 is exothermic and happens at lower temperatures. So we need to use fins to essentially remove heat. And the fins are very similar to what you would have designed in heat transfer class, for example. And so as we go around this drum, right, we get to about here, and we're all FeO. And then from there to there, we are going to use fins to remove heat and reduce the temperature. Now, after you reduce the temperature in this process, you expose it to water. And FeO plus water is able to undergo an exothermic reaction that converts the oxide back to the magnetite phase and releases hydrogen from the water. So you take up the oxygen, you release the hydrogen. So the total reaction here is actually just in a cycle is that water goes to hydrogen gas plus 1/2 oxygen gas. Okay, and then this is going to be exposed to water at the lower temperature until you get to about here. And then we start the cycle again where the solar energy is used to heat up the Fe3O4 and then decompose it back to FeO. And you do this over and over and over again. And so if you think about this, we really have a 3-step cycle that we have the heating and decomposition of FeO of Fe3O4 to FeO. Then we have a cooling step of FeO from a higher temperature to a lower temperature. And then we have a 3rd step where we introduce water into the system and we exothermically convert water and FeO to hydrogen and the magnetite phase, right? And we do this over and over and over again. Okay, so before we move on and even talk about anything else, I just want to ask you guys if you have questions. Is there anything that's sort of unclear about what's happening here before we do anything that's even marginally more complicated?
So the top reaction, is it driven by sunlight, or what is the sunlight doing?
Yeah, so the sunlight is just energy that's added. So you could run this cycle if you had waste high thermal energy, for example, also. It doesn't have to be solar, but solar is basically like Q in, right? We're just adding heat to the process there. And we're taking heat out here, and we're also going to have to take heat out there because we're going to assume that it's isothermal. Right, so we're going to take heat out in 2 locations, and we're just going to add heat in the form of solar energy.
Gotcha.
Right? Good question. Yeah,
and
good question.
What's causing it to rotate?
It's just on it's just on a shaft, and so you're actually just using a gear to turn it slowly. So you have to do work to turn it.
Got it.
All right, good question. And in the context of this, if we were assuming that the conversion was, 100%, it's obviously moving very, very slow. Now, one of the things I would like to ask you guys to do is that I sent you all a message this morning on Blackboard that had this paper attached to it. It would be really nice if you guys could read the paper and they talk through some of the actual physical parts of this, how they actually built one. So how do we build it and that kind of stuff. Also, quiz 8 will be based on the paper. So there's like 5 questions about the paper that is a part of quiz 8. The paper's not incredibly long, so hopefully it doesn't take too long to do that. Okay. All right. Any more questions about sort of this module before we actually talk about the problem we're going to solve? No? Okay. All right. So what we're going to do is we are going to create a combined cycle. And we talked about a combined cycle, in the context of having a Brayton cycle and a Rankine cycle. And here we are going to make a combined cycle out of 2 things. One is this solar-driven engine, right? We're going to input sunlight and water, and we're going to exhaust hydrogen and oxygen. But then you have to think about what would you do with hydrogen and oxygen? Well, hydrogen's a really great energy carrier. So, maybe you could just accumulate hydrogen that then you could use later for transportation. And with that in mind, we really want sort of a almost wells to wheels type of efficiency, or maybe we'll call it wells to, or like river to to engine efficiency. So we're going to utilize the hydrogen and oxygen. So the second part of this combined cycle is going to use a piston cylinder that operates like an Otto cycle that takes in hydrogen and oxygen and air, and I'll explain why in just a second. And it's going to burn it. So we're going to use solar energy to convert we're going to use the first cycle to convert solar energy to chemical energy. And then we're going to use the Otto cycle to convert the chemical energy into mechanical energy. And that's our combined cycle. Okay. And to do this, to actually solve a problem, let's put some numbers to what it is we're trying to do, and then talk about the individual steps that we're going to attempt. So in the problem that we're going to solve, we're going to assume, first of all, that liquid water is fed to a heater where it's vaporized and preheated to 100 degrees C before being fed to the process. So water sort of coming in to the solar cycle as steam at 100 degrees C. And before it gets there, we have to do a little heating step in order to take it from the river or wherever the water comes from to vaporize it, okay? That the reaction where the Wüstite phase becomes the magnetite phase, right? So this is the reaction with the water. We're going to assume that that reaction occurs isothermally at 330 degrees C. The next thing that we're going to assume is that the solar-driven reaction of the magnetite phase to the Wüstite phase occurs isothermally and at 1980 degrees C. We're going to assume that all reactants are present stoichiometrically and all reactions go to completion. That this act of rotating the metal oxide monolith consumes a negligible amount of energy. So we're going to turn it really, really slow, and we're going to assume it's not really heavy, although we will calculate the actual mass before we finish this problem. We're going to assume that the hydrogen and oxygen are produced in the solar water splitting part of the cycle at 1 bar, and it's delivered to the Otto cycle at 1 bar. Then between the hydrogen and oxygen being formed, right, this is going to happen at especially the oxygen side, because the oxygen is produced in the reaction that occurs at 1980 degrees C. The temperature is going to be pretty hot. So if we were to directly feed that into an Otto cycle and then combust pure hydrogen and pure oxygen, the temperature would be crazy high. And we couldn't really have materials that could handle temperatures that are as high as we would calculate. So what we're going to do is bleed in air in order to bring the temperature into the Otto cycle down to 100 degrees C. And in our heat engine, we're going to use a compression ratio of 12:1. Okay, so these are all the things that we're going to assume. And now we're going to sort of systematically start to analyze this process, right? This combined cycle. And the first thing that we're going to do together is we're going to draw a process flow diagram and label the mass and energy inputs and outputs and all of the unknowns. It's a lot. It is. Then we are going to step through solving the flow rates, temperature, pressure, and specific volume of gases or other components in each stream. And we're also going to determine the heat and work that are flowing in and out of every component in our flow diagram. We're going to determine the maximum efficiency for the combined process. And really all that means is that when we get to the Otto cycle, we're going to assume that the compression and expansion are adiabatic and reversible. So we know that those will be isentropic. And then after we're able to do all of this, we're going to try to determine if this technology is reasonable for like motive applications and talk about some practical ways when you build one that you can increase the efficiency compared to what we calculate. Okay, so if that sounds good to everybody, let's go ahead and start to solve this problem. And the first task here is to draw an overall process flow diagram. And so I'm going to start there. Okay, and I want to start with the 3 parts of the solar cycle. So I know that I'm going to have this solar side, and we're going to have the auto side. Okay. And the solar side, we said, has 3 stages, and we're going to preheat the water. So I'm going to draw the 3 stages just as 3 boxes, right? So there's 1 box, 2, and 3. Okay. And these represent each one of those stages. And so we're going to flow in this direction and to here. Okay. And when I think about this, the solar part is the stage here in the top left, just like was drawn on this slide up here. So step 1 is really this one, or the step here at the top left. Okay. And so that we know is operating at 1980 degrees C. So we know that the temperature in that stage is 2253.15 Kelvin. And we know that there is some amount of heat that we're going to call Q solar that comes into the process, and that's unknown. Okay. And so then moving clockwise, then obviously this box here is a representation of the fins. Okay. And so we have Q fins, and we also don't know what that is. Now we know when we reach the fins that we're completely FeO, right? We're completely the Wüstite phase. And because this thing is spinning, we're going to represent the spinning rate as a flow rate. So we're actually going to say, when you get to here, the flow rate of FeO is also unknown. And then when we leave the lower temperature part of this process, where our temperature is equal to 603.15 Kelvin, that we are completely Fe3O4. So the flow rate of Fe3O4 is also unknown. Okay. Now the diagram, of course, is missing a couple things. We know we're going to end up with oxygen and hydrogen coming out of here, but we'll get to that in a second. We also haven't fed water into this system yet. So let's do that really quickly. Okay. So we're going to have some sort of heater where water comes in and is fed to the process. So we know that the temperature that is leaving the exchanger but is entering our system is 373.15 Kelvin. Now, we don't yet know what the heat is that's added there. And we also don't know what the flow rate of water entering the system is. So that's also unknown. Okay. Now, we were told that the process to convert FeO to Fe3O4 was exothermic and isothermal. So we're obviously going to have to remove some heat as well. So we're going to say Q for our reaction is also equal to 0. Okay. So we're almost there, right? We're almost to the auto cycle side of things, all right?
Sorry,
So
was that Q reaction unknown or 0?
no, it's unknown. Did I say 0?
Okay,
I'm
you said
sorry, it's
0.
unknown. Yeah, I'm sorry. So, all right, now we have to produce hydrogen, or at least take the production of hydrogen and oxygen into consideration and then feed this into the Otto cycle. So I'm going to make a little mixing box here. And here's where our hydrogen is going to go. And there's where our oxygen is going to go. Now, we actually don't know yet what the flow rate of oxygen is. And we don't yet know what the flow rate of hydrogen is. Right? So we don't know those two things. The next thing that we're told is that before going into the Otto cycle, we were going to cool the gas down. And we're going to do that by feeding air. And we're going to say that the temperature of the air that's coming in is 25 degrees C, so 298.15 Kelvin. But we don't know what the flow rate of the air is. And I'm actually going to break this up into the flow rate of nitrogen and the flow rate of oxygen. And I just do that because we know later in the Otto cycle, oxygen is going to combust. So we're actually going to take the combustion of oxygen into consideration, and we're going to do something we haven't done before, and that is look at the composition and the heat of combustion of a fuel instead of treating it like a closed cycle like we have in the past. And so then we have a stream that flows out of this mixer at a temperature of 100 degrees C, right? Or 373.15 Kelvin. And the first stage of the Otto cycle is compression. And we were told that we are going to assume that it is adiabatic and reversible, right? Or delta S is going to equal 0. Now, of course, we're going to have to do some work, right? So we're going to call that WC1, where C just stands for compressor. And I know there's only one compressor, but that's how I chose to name it. Then after the compression, we're going to go into our combustion chamber. And we were told that the compression ratio was equal to 12 inside of the compressor. So in order for us to figure out the final temperature, right, we know that V out for the compressor, or actually a better way to do this, is that V in for the compressor over V out for the compressor is equal to 12. And the things that we're going to have to solve for are the same things that we did when we solved for the Otto cycle the last time. We're going to have to find the temperature and the pressure at that intermediate state. And then we're going to combust all of the oxygen or all of the hydrogen, right? And we fed in excess air, so there will be oxygen that's left leaving. So now we have to calculate several things leaving the combustor. So the first one is the temperature. Then we also need to know the flow rate of oxygen that's leaving and the flow rate of hydrogen that's leaving, as well as the pressure leaving the combustor, right? So that's unknown as well. And then finally, these hot gases are going to be expanded, right? So we're going to have an expansion. And that is where we're going to get work, right? So work out is equal to a question mark. And leaving our system, we'll have gases that are at some temperature and pressure that we will determine, okay? So the temperature leaving the expander we'll figure out, and the pressure leaving the expander, okay? And this is the process flow diagram. Maybe I can fill in one or two more little pieces of information, right? So here we know that in the combustor, the volume is constant, right? It's isochoric. We know that we've treated the combustors or reactors as adiabatic in the past. The expander, right? It's a piston cylinder device. So the volume at the end of the expansion is equal to the same volume that we had in the combustor, or sorry, in the compressor. And finally, that the change in the entropy, because it's reversible and adiabatic, is equal to 0. Okay? And here's all of our variables that we're going to step through and solve for. Now, before we start to do that, we need to think maybe a little bit about the end game. And the thing that we want to calculate is the efficiency, okay? And how did we define efficiency so far for every other cycle?
Negative work net over Q in.
Okay. So is that a fair definition for this process, do you think?
Seems reasonable enough.
I don't see any reason to change it, right? The purpose of this process is still to do work based on taking in heat, right? So let's look at this. Well, where is work done or extracted in this process? Well, the work still just occurs on the Otto side, right? Just in the expander and the compressor, right? So we'll get some work out from here and some work will have to be done there to actually compress the gas. But the only other work that we could have considered is the work that it might take to rotate the drum. But quite frankly, I couldn't find a reasonable estimate for that. And it's not going to be really heavy and it's going to be moving very slow. So I thought, okay, compared to a compressor, this is going to be fine. So we're going to neglect that. So we only have two sources for our work terms. And what about Q in? So where do we add heat in this process?
Solar and then the combustion.
Now the combustion is really interesting. So usually, right, we added heat in that step, right? We had Q in. But we already did that, right? Isn't Q in just Q solar? Right? The whole idea was to take in solar energy and convert it into chemical energy. And we did that. So actually Q in, like that you would think of as the combustor, we already took into consideration here when we split to make hydrogen. It's just that that thermal energy is now harnessed and stored in the chemical bonds for hydrogen and oxygen. So that's already taken into consideration. Now, where else did we add heat?
When we were heating the water, preheating the water.
Yep, excellent. So in this process, the efficiency then is just minus the work of the expander plus the work of the compression divided by Q solar plus Q W. And so our task is to then calculate those values. And we're going to do that by systematically stepping through the solution of each one of these unknowns that are currently question marks. Okay. What would ordinarily be part of a project assignment would be to do a systems level degree of freedom analysis. Now, to save time, I'll give you the result of that degree of freedom analysis, that, essentially we have 1 degree of freedom that is left given the problem statement. And there are some things that we could choose as pieces of information to know that may be more or less helpful. Okay. So, you could be asked, you could be asked how to make a certain amount of work, or what's the system size to do a certain amount of work. But I find that when I am confronted with a problem like this, where I have 1 degree of freedom, I prefer to choose a basis to solve the problem. And then once I choose that basis, then I can always solve for all of the work and energy inputs and outputs, and I could always just linearly scale that problem. And I like to do it in a way where it's very easy to follow. So what we're going to do is we're going to choose a basis where the flow rate of water that is entering our thermochemical cycle, right, the solar cycle, we're just going to say that that is equal to 1.0 moles per second, okay? And that eliminates that 1 degree of freedom. And the thing that's really nice about that is we're going to be able to first use the reaction stoichiometry to find all of the other flow rates on the right-hand side here. So I'm going to first solve for everything on the right-hand side in this sort of solar part of our combined cycle. Then we'll move into this box here, solve for that, and then we'll move into the Otto cycle and do the compression, then the combustion, and then the expansion. So let's start with the molar flow rates. I think that's the easiest thing for us to do. And if we know that the flow rate of water that's entering is equal to 1 mole per second, well, let's take advantage of our first reaction, where we know that the stoichiometry is that 3 FeO plus water gives us Fe3O4 plus hydrogen. And remember, we're assuming that all of the reactions in this problem undergo those reactions to completion, and that all the reactants are available stoichiometrically. So that makes this problem actually relatively straightforward. So if this is our equation, well, now if we have 1 mole of water per second, we know, therefore, that the flow rate of FeO into the process is just 3 times the flow rate of water, and that's equal to 3 moles per second. And both Fe3O4 and hydrogen are 1-to-1 on a molar basis with the water that's in this equation. And so, therefore, we also know that the molar flow rate of Fe3O4 is equal to 1 mole per second. And we know that the flow rate of hydrogen is equal to 1 mole per second. And so just using the reaction stoichiometry, we now have almost all of the flow rates. To get the other one, we need to look at the reaction that's happening on the top side of the solar cycle, where if you remember that Fe3O4 reacts or thermally decomposes to give us FeO back and 1/2 oxygen. So if we look at the stoichiometry here, that for every mole of Fe3O4 that comes into the solar compartment, we make 1/2 mole of O2. And so because of that, the flow rate of oxygen is equal to 0.5 moles per second. And of course, this also would make sense because we know the overall process is just going to split water. And if we looked at this, right, the flow rate of water in should be equal to the flow rate of hydrogen, and that should be equal to 2 times the flow rate of oxygen, just given the reaction stoichiometry, right? So if we looked at the overall reaction, water gives us hydrogen plus 1/2 O2. Okay, so hopefully this all makes sense in the context of the reaction from your perspective. So if we look at where we are in this process, so we have now all of these flow rates. So we know here, and if we're going to track this, right? So the flow rate of water in is equal to 1 mole per second. So we know this flow rate of FeO is just 3 moles per second. We know that the flow rate of Fe3O4 is 1 mole per second. And we know that the flow rate of hydrogen and oxygen are 1 and 0.5 moles per second, respectively. Okay. So now what we need to do is to find all of these Qs, right? So we need to find sort of Q fins, Q water, Q for this reactor. Remember, that's isothermal and exothermic. And then, of course, the most important one here is Q solar. So let's start picking those off one at a time. And if you think about the energy balance for each one of those steps, right, our energy balance really simplifies to just Q is equal to, and we have an open system where things are flowing, the sum of the enthalpy out times the mass flow rate out minus the sum of the enthalpy in times the mass flow rate of those species that's coming in. So if we look at the fins, for example, in this problem, in our process flow diagram, remember that when we get to the fins here, that the only thing that enters the fins is FeO. And the only thing that leaves is FeO. And so if that's the case, then the heat for the fins are just equal to the flow rate of FeO times the difference in the enthalpy. And so to figure out the difference in the enthalpy, we need the heat of formation of FeO at the temperature of interest. And remember that we said that the temperature there was 603.15 Kelvin, and that's minus the enthalpy of formation of FeO at the entering temperature, which was 2253.15 Kelvin, or 1980 degrees C. Okay. And now the question is, where do we get these heats of formation from? Well, if you remember that the heat of formation at any temperature equals the initial heat of formation, right, at some reference temperature, plus the integral from T0 to T of Cp dt. So we need some information then about the heat capacity as a function of temperature for FeO. And one of the places that we've looked to during our semester is the NIST chemistry webbook. And that's exactly where I looked here. And so you can see that I have all of the NIST parameters for both phases of Fe3O4 that were available in NIST. And so from there, I'm able to find the heat of formation for FeO at both of these temperatures. And you can see those written right here. And so if we take those two values and simply subtract them, we find that Q fins equals the molar flow rate of FeO, so that's 3.0 moles per second, times the heat of formation at 603, and that was minus 256 kilojoules per mole, minus a negative 127.8 kilojoules per mole. And then we can find that the heat that has to be removed in the fins is equal to minus 384.7 kilojoules per second. Okay, so there's Q fins. And now we're going to do the same thing with to find Q solar. Okay, and if we want to find the heat that's coming out in the solar portion of our diagram, let's look at what comes in and what leaves. Well, essentially what comes into the solar compartment is Fe3O4, and what leaves is oxygen and FeO, right? And so oxygen and FeO leave at this higher temperature because that's the reason we need the fins. And Fe3O4 comes in at the lower temperature. So if we look at this and we use the same energy balance, that Q is the sum of the enthalpy out, m dot out minus the enthalpy in times m dot in, well then Q solar simply equals the flow rate of FeO, that is in the process, times the heat of formation for FeO at 2253.15 Kelvin, plus the flow rate of oxygen that we solved for, times the heat of formation of oxygen at that temperature, minus the flow rate of Fe3O4 times the heat of formation of Fe3O4 at the lower temperature. Okay. And so, of course, the solids, we already talked about finding the heat of formation of those solids. But I've also done the same thing here with the gas phase data. And you can see here on the bottom left, I have all of the temperatures, right? I have the cold temperature, I have the hot temperature. I also have the temperature of the mix that's going to come out of the mixer that we're going to have to find, as well as the other temperatures that we'll find along the way here. And then I'm able to find the heat of formation for oxygen at the higher temperature, which is 68.8 kilojoules per mole. So let's use the data from those two spreadsheets. And so again, we know the flow rate of FeO is 3 moles per second, times the heat of formation at 2253, which is minus 127.8 kilojoules per mole, which we just used in the previous problem, plus the flow rate of oxygen, which is 0.5 moles per second, times the heat of formation of oxygen at that temperature, which we just saw was 68.8 kilojoules per mole, then minus the flow rate of Fe3O4, which was 1, times the heat of formation at the lower temperature, which is minus 1065.6
Could you just scroll down a
kilojoules
little bit? Sorry.
per mole. Yeah, sorry, can you guys not see that?
It was like covered up by the bar at the bottom of my screen.
Yeah, there we go. So then Q solar then equals 716.6 kilojoules per second. Okay. And now we really just have two other Qs to do on the right-hand side of our diagram. So the next one that I'll do is Q water, which is just equal to the flow rate of water that's entering the system, right? And Q water is in the preheater. Then that's times the heat of formation of water at 100 degrees C in the gas phase, right? Minus the heat of formation of water at 25 degrees C in the liquid phase. And so then Q water is then just equal to 1.0 mole per second times the heat of formation, which is 239.3 kilojoules per mole, minus a negative 285.83 kilojoules per mole. And so we also find that Q water is equal to 46.5 kilojoules per second. Okay. And then the last one that we need to find in our process is the heat that we have to remove in the lower chamber, right, at the lower temperature, because it's done at isothermally and it's exothermic. Sorry there, I porky pigged that one a little bit. So QR, then is equal to, right, the sum of the flow rates times the heats of formation in minus the sum of the flow rates times the heats of formation that are leaving. And so if we think about it this way, then we have the flow rate of hydrogen times the heat of formation of hydrogen at the lower temperature, right, plus the flow rate of Fe3O4 times the heat of formation of Fe3O4 at the lower temperature. And then now minus the stuff that's that was entering. So that's the flow rate of water that was entering at 100 degrees C, right, in the gas phase. Then minus the flow rate of FeO times the heat of formation of FeO at the lower temperature. Okay. And so then we can put in the values for these. And what we'll find is that that is minus 49.35 kilojoules per second. Okay. All right. So before we do anything else, does anybody have questions about this? About, you know, how we calculated all these Qs, setting a basis, anything like that? Okay. If not, let's look at what we've done. Well, now we have that, we have that, we have that, and we have that. So the only thing that's left on the right-hand side of this combined cycle for us to figure out are these last two flow rates of nitrogen and oxygen. And if you remember when we talked about this earlier, that the whole thing that we're trying to do here is that if you were to let a very, very hot gas enter the compressor, that compression would go to an extremely high temperature, then the combustion would be even hotter. So we have to cool this down a little bit before we start to burn the hydrogen that we just made. And the way that we wanted to do that was to just mix in air such that the temperature leaving this box is 100 degrees C. And we can do that adiabatically, right? So we can have this box where we're mixing in adiabatically. And the result there, if you think about it from an energy balance perspective, right, that remember dNu dt is Q plus W plus the sum of H in m dot in minus the sum of H out m dot out plus 1/2 m dot times V in squared minus V out squared plus m dot times G times Z initial minus Z final. That if we looked at this, well, if we're at steady state and we're going to mix these adiabatically, we're not doing any work, and the gas velocities will be similar and the height will not be significantly different. So the result of our energy balance here is really just that that 0 is equal to the sum of H out m dot out minus the sum of H in m dot in. And I know I flipped those and I did that on purpose because it doesn't matter because there's 0 on the other side here anyway. So that's our energy balance. And if we think about what is going in the box and what is leaving the box, well, leaving the box will be some flow rate of oxygen, right, at 100 degrees C, right? Then plus some flow rate of hydrogen, also at 100 degrees C, plus, because we're feeding air, some flow rate of nitrogen at 100 degrees C, okay? So that's all the stuff that's leaving the box. And actually, sorry, this was our flow rate of oxygen. We also have a flow rate of oxygen because of the air that we fed. And that is F nitrogen over 4, right? Because it's approximately 80-20. Again, times the heat of formation of oxygen at 100 degrees C. Sorry, that's all the stuff that's entering or leaving, minus the stuff that's entering, okay? And so entering, we had some flow rate of oxygen times its heat of formation. And remember, that's really hot. It's really the reason we have to cool this down. And then also entering our box is hydrogen at 600 Kelvin. And then we have nitrogen entering at 25 degrees C. And we have this F nitrogen over 4 times the heat of formation of oxygen at 25 degrees C, right? So that's all the stuff leaving minus everything that's coming in. And if you think about this, we already solved for FO2, FH2. And so the only unknown in this equation is the flow rate of nitrogen, and it actually shows up 4 different times here. So what we have to do is to put this thing in Excel and just have GoalSeek manipulate the flow rate of nitrogen until we satisfy the energy balance, right? Or where Q is equal to 0. And if we do that, we find that the flow rate of nitrogen is equal to 14.6 moles per second. And then the extra flow rate of oxygen, right, that we added is 3.65 moles per second. And so if you wanted to look at it as a flow rate of air, that's 18.25 moles per second, right? But these are the unknowns that we labeled before, okay? All right, so while you guys are writing, does anybody have questions about like how we did this or how we got here? No? All right, if that's the case, I'm just gonna scroll back up for a second and look at where we are with the diagram, okay? So now we have this one and we have this one. And so in this process, we now need to work on the compressor. And we know we're going to do this adiabatically and reversibly. Now, the way that I looked at this is that it's actually somewhat difficult for us to talk about just the specific volume. And so when I was solving this problem, I thought, you know what we're really going to do when we do this compression is we're going to change the volumetric flow rate, right? Because, or the effective flow rate, even though we usually treat the Otto cycle as a closed system. So we're going to do something that's kind of weird. We're going to actually talk about things in terms of flow rates, but knowing that the Otto cycle, the calculations we have to do based on the assumptions for the Otto cycle are a closed system. And so this is going to feel a little bit uncomfortable, and that's okay. So the first thing that I think we should do is that because nitrogen, hydrogen, and oxygen are all going to be treated in exactly the same way, let's actually calculate the total molar flow rate, okay, that is entering. And that is actually the flow rate of oxygen plus the flow rate of hydrogen plus the flow rate of oxygen that we added plus the flow rate of nitrogen, right? And the flow rate of oxygen was 0.5, hydrogen was 1, FO2 add is 3.65, which we just solved for a second ago, and nitrogen is 14.6. So if we add that up, the total molar flow rate is 19.75 moles per second, okay? And now if we want to look at this in terms of volume, we can use the ideal gas law. So PV is equal to nRT, right? Or B is equal to nRT over P. And so we know that's 19.75 moles per second times 0.08314 liter bar per mole Kelvin times 373.15 Kelvin divided by 1 bar. All right, so before we compress it, we had been told in the problem statement that everything was at atmospheric pressure. So our volumetric flow rate that's entering the compressor is 612.5 liters per second. Okay, so that's like, we'll call that V1, right, which is entering the compressor. Or the compression stage, right? And V2 is just equal to that number divided by 12, because we were told in the problem statement that the compression ratio was 12, and that's approximately 51.0 liters per second. And that's exiting compression. Okay? And we were told, just like in many of the other problems that we have solved throughout the course of our semester, that the compression is done isentropically. And so we know that delta S over R is equal to, and we've used this a lot over the course of our semester, actually, that we had delta S over R equals, for a multi-component system, it would be the sum of the individual moles, but here we're going to use the flow rates, times the integral from T0, or we'll call it T1 to T2, of CV over R dt over T, plus it would be actually the sum of all the FIs times the natural log of V2, and it normally would have been V2 over V1. Well, if we're going to do this for our problem, we need to consider a couple of things. So first of all, we know that that's going to have to be equal to 0. Here's a couple other things that are going to change. The first one is that if we're going to treat this as with these effective volumetric flow rates, we can do that, and we didn't break any rules. And the other thing here is that the sum of the FIs are just F total, right? It's that total mass flow rate. So I actually labeled it as N total, right? Okay, so that's okay. So our instinct is probably to use the NIST data if we know that delta S has to be equal to 0. And you would think, yes, we can use the NIST data to get this value, because the NIST data takes the temperature change into consideration. But the weird secret about the NIST data is that it's actually done at constant pressure. It's not done at constant volume. And so this integral that you get from the NIST data is actually the integral from T1 to T2 of Cp over R dt over T. And we learned throughout the course of our semester that this is actually just the integral from T1 to T2 of Cv plus R over R dt over T. And so what that means is that if I actually want the integral from T1 to T2 of Cv over R dt over T, that's just equal to the integral from T1 to T2 of Cp over R dt over T minus the integral of R over R, or just 1, from T1 to T2, oops, sorry guys, to T2 of dt over T. right? Because CV, the R over R term goes there, okay? So the interesting thing when you're solving this problem is that this is the NIST data. So the actual thing that we need, so that's the NIST data, right? So now, if we're going to calculate the change in the entropy using the NIST information that we had before, because we don't really have a straightforward expression for CV yet, we're going to come up with this equation where delta S over R is equal to the sum of Fi times delta Si NIST plus the total flow rate times the natural log of V2 over V1, right? That's just this. And I'm sorry, I used F again. And then minus N total times the natural log of this thing that we're going to call T2 over T1. And that might be really weird for you guys. I know the first time that I solved this and the first time that I solved this as part of a project with other folks, this was actually a very confusing part of the problem. But hopefully it makes some kind of sense to you, because the integral that NIST takes is the integral of CPDT, and they just hold the pressure constant. And so hopefully this correction makes sense. Okay, so if that's the case, this second temperature here that we've labeled is what we called in the original diagram just TC1. It's the temperature that was leaving the compressor. So what we can then do is find where that temperature, find the temperature that satisfies this equation. And you'll notice in the Excel file here, not only have I calculated the enthalpies at these different temperatures, right? So here's TC1, but also the NIST entropies at that temperature, all right? And so essentially what I'm going to try to do in this auto calculation is that I have a delta S equals 0 cell, and I just iterated the temperature until delta S equaled 0. And what you find is that that temperature, TC1, equals 941.25 Kelvin. And then we also know, if we know the total flow rate, the temperature, and the specific, the volumetric flow rate there, we also can find the pressure leaving, and that's 30.26 bar. And that means to do this compression, right? If we think about the device on a larger scale, well, if we treat it as a closed system, delta U is equal to Q plus W. Well, the Q is equal to 0. So the work in our compressor is actually just equal to then the change in the internal energy, which is the sum of the flow rates entering, or leaving, times the internal energy of those species leaving, minus the sum of the flow rate of that species entering times the internal energy of that species entering. And so if we do that, we can actually easily find the changes in the internal energy and find that WC1 is then equal to 253.45 kilojoules per second. So we actually have the work term for the compression. Okay. All right, I know the problem's kind of complicated and we're moving a little bit fast through it, but essentially we've now done the compression. So let's do the combustion chamber. And then we'll do the expansion, and then, I'll pause, we'll answer questions, and then we'll just talk about a couple other points. So to do the combustor, I actually started with an ICE table, because we're going to do the same thing we did in, let's say, the methane problem that we had earlier in this semester, where we're going to assume that it's adiabatic and that no work is going to be done. So actually, in this case, instead of delta H being 0, delta U is going to be equal to 0, because we're going to treat it like a closed system. But we know that for our ICE table, we have hydrogen, oxygen, nitrogen, and water, right? And entering, right, we know that that's 1. We know oxygen was 0.5 plus 3.65 that we fed in with the air. We solve for that, and there's no water at the beginning, right? So at the beginning, this is 19.75 moles per second. So we know that's -1, right? Because we're going to fully combust the hydrogen. And so the stoichiometry for that is -0.5. No nitrogen reacts, and we're going to make 1 water. So we lose a half overall. And so we have no hydrogen left at the end, 3.65 moles per second of oxygen, 14.6 for nitrogen, 1 water, which gives us 19.25 moles per second at the end. Okay. And one of the things that I did in Excel was that I know, because of the energy balance, right, that there's no work, there's no heat that's being added, that the temperature is going to go up simply from the combustion. So if you know that the internal energy of formation at any temperature is just the heat of formation at that temperature minus R times that temperature, then we can find that 0 equals the sum of F out of any of the species times its internal energy of formation at T out minus the sum of F in times the internal energy of formation for that species that's entering the combustor. And so we had labeled this in our original diagram TC1, which we just calculated. In the original diagram, we labeled that TC2. And so that's why, if you noticed in the Excel spreadsheet, in the phase, in the gas phase thermochemistry data, I also calculated the internal energy of formation at those temperatures. And you'll notice that that's really just equal to minus R times T, right? It's the change in the internal energy minus RT, which you can see in the equation cell all the way at the top. And I did that for nitrogen at all the temperatures, oxygen at all the temperatures, and the water at the 2 temperatures that we're actually interested in. And in this case, you're just changing the temperature until Q is equal to 0, right? Because there's no heat that's being added to the process. There's no work being done. And so that's our check that we're actually correct. And so if we do that, we find actually that TC2 leaving the combustor is equal to 1425 Kelvin. And we also could calculate the pressure, because we know the specific volume, we know the final temperature, and we know the final number of moles. And so the pressure there is 44.65 bar, okay? And without belaboring the point, because I want us to actually be able to talk about this a little bit, we can do the exact same calculations that we did in for the expansion as we did for the compression. And we'll find, and it really is the same calculation, just the flow rates are slightly different, and the now the final temperature, the initial temperature is the temperature leaving the combustion. We're solving the final temperature. But then the temperature leaving is 621.48 Kelvin. And the final pressure is 1.62 bar. And we can find the work as well. And that's minus 389.96 kilojoules per second. And that's really the important point here. Okay. So, and I'm sorry that, the math is exactly the same as the compressor. So I took a little shortcut in the interest of time. So let's find the efficiency, okay? But before I do that, I want to give you guys a chance to ask questions about this or this. Does anybody want to come in and ask a question really quick? All right, so we said the efficiency was minus the net amount of work over Qn. And that was equal to minus the work that we got from the expander plus the work that we had to use to compress the gas over QW to preheat the water plus Q solar, okay? And so that's equal, if you take our numbers, to minus 389.96 plus 253.45 divided by 46.54 plus 716.64. And that is an overall efficiency equal to about 18%. Okay. All right. So then we were asked, after we determined the efficiency, to think about maybe ways that we could increase the efficiency and also to figure out if the technology may be reasonable for a motive application. Okay. So let's do that top one first. If it's reasonable for a motive application like a car. So does anybody want to come in? What are some of the considerations when we think about whether it would be appropriate for automobiles?
Well, it needs to
Weight.
be small for sure.
All right, I heard weight and size, right? Perfect. I think those are two very, very excellent things. So here's what I did. I took the net power from here, okay? And if we do that, work net is equal to 136.5 kilojoules per second, which actually is approximately equal to 180 horsepower. So it turns out that I did not plan this. I won't lie to you guys. I just guessed 1 mole per second and it happened to work, right? And 180 horsepower would that car would have some oomph to it, right? So what I then did is I took the flow rate of FeO and I converted that to a molar flow rate of FeO, or sorry, a mass flow rate, and it became about 0.215 kilograms per second. And I did the same thing with the flow rate of Fe3O4, made that a mass flow rate. And that was, and I looked up their density and all of that stuff and molecular weight. And so it's 0.447 kilograms per second, okay? Now, of course, it's mounted on this huge wheel. Well, not huge, but it's mounted on a wheel, okay? And hopefully you guys had a chance to read the paper. Remember, the quiz is on the paper this evening. And there's a lot of extra mass that is involved. The fins weigh something. The actual substrate weighs something. So here's the thing that I assumed, that the active mass fraction was around 5%, okay? And I had to assume some kind of rate that this thing moved around, and I guess that's where this number came from. And when I finished doing that, I calculated the mass of the system in kilograms to be 8.9 kilograms to get us 180 horsepower approximately. That's not bad, right? Right, the engine in your car certainly weighs more than that.
Is this an actual real thing?
Well, I mean, that's an approximated number. I don't know how good 5% is, but even if it was 1%, I mean, it would still be about 1% would get you about to where the engine in your car is, with a lot of extra added mass. But here's the thing. When we talk about size, right, we might think, oh, what's the size of this thing? But that's not the most important size that we have to think about. What's the most important size to think about in this problem?
The mass of the apparatus
What do you mean by the apparatus?
or the engine?
All right, not the engine though. What
Wouldn't
is
it
actually?
depend on how sunny it was that day?
Great comment. So let's think about this. So in Columbia, okay, right? We're in Columbia, South Carolina. We get an average amount of solar energy of 5.16 kilowatt hours per meter squared per day. Okay, and I'm going to multiply that by 1 day has 24 hours, and that means that we get 0.215 kilowatts per meter squared in Columbia. Well, we already know, right, so if we were to think about the area here, right, this equals Q solar in our problem divided by what we get from the sun. And in our problem, we calculated this was 716 kilowatts, right, or kilojoules per second, divided by 0.215 kilowatts per meter squared. And that is 3,333 meters squared, which for those who don't love the metric system, that's about 35,860 square feet. So what's the thought on that?
I don't think you're going to be able to move a warehouse with 180 horsepower.
Yeah, no way, right? Actually, that's a huge area. You think that's, you'd need a huge wide open field collecting solar power that then concentrate it and beam it to your car wherever it happened to be. And, I'm not super negative on solar or anything, so I don't want to make it sound that way. But one of the things that really has to be considered with solar is surface area and where, right? So where do you generate that power? So, yeah, I mean, somewhere in the desert, I mean, people do these things where they have a map and they say, hey, look, if this corner of Nevada was all solar panels, it would give us all the electricity that everybody needs for the whole year. So yeah, I mean, I get that. But yeah, I mean, this certainly isn't going to work for a vehicle application. So it's an interesting question. Here we're able to convert through solar thermal, we're able to get to 18%. And for a while, that would have beaten solar PV, right? Because then we would have used the Otto cycle to actually make electricity. We wouldn't have used it to power a vehicle. There are possibilities that doing this might be cost competitive on a larger scale, but the cost and efficiency of solar is coming way, way, way down all the time. So solar PV might actually completely win over a system like this, but it's sort of interesting. The other thing while we're talking about efficiency is how do we increase the efficiency, right? So if we look at the overall process here, there's a couple of ways that I could think of to do this. I mean, one thing is that it seems silly to me that, you would have heat that you have to remove from these fins, and you would separately heat the water, right? That you'd have some other mechanism. If I were going to do this, I would actually just feed this into there, right? And exchange heat to preheat the water. And that would reduce the amount of heat you had to remove in the fins. And it would eliminate this from our efficiency calculation. So we'll take a look at that in a second. The second thing we could do is increase the compression ratio, right? Because we know that increasing compression ratio improves efficiency. And the second thing is we have to heat this to such a high temperature for the thermal decomposition. And if you read the paper, the minimum temperature that you could heat to is 1600 degrees, right? And right now we're heating Celsius, which is 1873 Kelvin. And right now we're going all the way up to 1980 degrees C. So, you know, I redid all the math in Excel, which actually in Excel is pretty easy. It's a couple of goal seeks and you're done. But if we actually do this where we, you know, we use Q fins to preheat, or how about to provide QW, then our efficiency just becomes equal to minus the net amount of work divided by Q solar. And if we do that, the efficiency becomes equal to 0.19. So 19%. So that would increase the system efficiency by 1%. So if we also increased the compression ratio to 18, independently, right? The only thing it does, the efficiency is 0.194, right? So we also increase the efficiency. And if we decrease the temperature that we have to preheat the solar to 1873 Kelvin, then the efficiency equals 0.200 actually. And if we do all of them, we can get the efficiency equal to 0.23. So the efficiency is still kind of low, but we do, through a combination of these things, change the efficiency or increase the efficiency by 30%. And I think, you know, this one is pretty easy to do. In a Otto cycle with hydrogen, this one is also doable. Compression ratios for internal combustion engines on hydrogen are actually higher. If you just did a little bit of background reading, 18 to 20 is not unusual. So that's fine. This one I actually think is the hardest one because the thermal decomposition is going to take time. And so this is going to really increase, I think, the size for that flow rate. But, you know, you could possibly get an efficiency that is, you know, just south of 25%. So I hope, you know, in the process of solving this problem, this is a huge problem, right, that we tried to solve in only 2 class periods. But I hope that what we did, you're not too uncomfortable with, because it took advantage of everything that we've done throughout the course of this semester, from ice tables and reactions to the results of energy balances and entropy balances. And, you know, as far as a difficult problem, right, we would have been using Excel and goal seek and all that kind of stuff to solve the problem as well. And hopefully you guys have had some good practice doing that during the course of the semester. And I think it's proof that any system that we come in contact with, we can use the tools that we've developed this semester to analyze them. And I hope that you guys, as you move forward, feel comfortable doing that.